Okay, in this class, we're going to rely on the ability to think proportionally. What does that mean? It means we're going to be working without numbers. We're just going to be thinking in proportion. So let's say I have two masses, and they are a distance of r apart from each other. Right? We're given information, and that's the only information we know. We know that they're two masses, they are r apart, and when they are this far apart, they have a weight, a force of gravity between them that is some number. Um, we might be asked like something like, what happens if we play around with the factors that go into this force? Like for instance, like what happens if we take mass, uh, this mass, and show it here, but then show this mass as being twice as far away from that first mass? So there it is, twice as far away. What happens to how much force there is between these two? How much gravitational force would there be when I move them twice as far away from each other? Well, that takes, like I said, the skill of proportional thinking. And here's how I do it. What I do is I take the formula of universal gravitation, and what I do is I indicate by how much each of these terms is changing from the old story to this new story. Well, the universal constant will never change, and I'm going to write that it's not changing. We're increasing it by a factor. We're not, it's not changing. So we're just going to put a 1 next to it. This mass is not changing, so it's going to stay 1. This mass is not changing, so it's changing by 1. This distance is doubling, so I have to change this by 2. And it's important that it's 2r. So this square needs to go outside of a set of parentheses. And then what I do is now I need to factor this out of my formula and pull it out. So what is 1 times 1 times 1 in the numerator? Well, it's 1. And that leaves me with g times m times m. And what is 2 squared? Well, that is 4. And what is r squared? Well, it's r squared. So essentially, by doubling the distance, what I've done is I have quartered the force of gravity between the two objects, because gmm over r squared is fg, right? Because fg was that. So whatever the force of gravity was, it is now 1/4 that, because I've doubled the distance. That's what the inverse square relationship does. And nature has tons of these. It happens with light, it happens with gravity, it happens with electricity, electric force. So nature loves this inverse square relationship. It's the story of an expanding sphere. The surface area of a sphere would increase fourfold when you double the distance. Um, so that's sort of what's happening here. Um, so let's try another one where we have the story of a mass and another mass that is r apart. And what I want to do is I'd like to triple the distance between them. So let's say it's now 3r distance. When we used to be fg apart, how much fg are we going to be now? Well, it's an inverse square relationship. I want to use my g m m over r squared relationship. Never going to change big G. In this case, I'm not changing the masses, so the masses stay the same, and R is increasing threefold. So factoring this out, I get 1 times G over M times M, and this is going to be 3 squared is 9 over R squared. So this is 1/9 times whatever the force was. So if this was, I don't know, 90 newtons of force between these two objects, this is now 10 newtons of force because I pulled them apart 3 times as far as they were. This is the factor by which it changed. It's not the new force, it's how much change there was compared to the previous scenario. All right, let's try one more. Distance isn't the only thing we can change. We can also change mass. So we have our original setting where we have mass and mass, and when that is the case, we have a weight between them or a force of gravity. Let's say that is 100 newtons when it's like that. Well, let's say I double this mass and I double this mass, but leave them in the same position they were. What would the new weight be? How much weight would there be, or how much force of gravity would there be between these? Well, I'm still going to go to my old relationship here. And what I'm going to do is I'm going to substitute in the factor by which this mass is changing. That's 2. And this mass is changing by twofold. And the distance remains the same this time. So let's factor everything out and figure out how much we're changing the weight by. 2 times 2 times 1 is 4. GMM. And of course, R squared is R squared, and 1 squared is 1. So it looks like I'm increasing the weight by a factor of 4. So if it was 100 newtons before, now it's going to be 400 newtons. So by doubling each of the masses, what I've done is I quadrupled the amount of force between them. We need to be able to think proportionally, work this way. So here's 3 examples that we did. I'd like you to do the homework and give it a try yourself.